Welcome to Introduction to Physics, Chapter 16. We'll start the semester with electric charge and the electric field. So you might remember back from Chapter 5 that we mentioned there are 4 fundamental forces in nature, and they include gravity, electromagnetism, weak nuclear force, and strong nuclear force. In the first half of the class, Physics 1110, we included gravity as part of that. In this term, we'll cover the next 3 fundamental forces, and we begin now with electricity. We'll talk about electricity in Chapter 16, then magnetism, and then we'll put them together. So electromagnetism will come together as a fundamental force of nature. Okay, having set that stage, here are the topics for Chapter 16, and for this recording, we will get up through just before Coulomb's law. So the first 4 topics: static electricity, electric charge in the atom, insulators versus conductors, induced charge, both by induction and conduction, as we'll get to. All right. And we'll get to these other topics as we move along. But I will comment now, since this is the first lecture for this term, that asterisked topics are generally not included in this course. They are extra material, but they often have biological applications. So if you are interested in biology, I definitely recommend you look those over. Okay, before we start, I thought I'd use the opening chapter question from Chapter 16. And it asks, if there are 2 identical tiny spheres and they have the same electric charge, if their separation is doubled, the force each exerts on the other will be. So think this through. So I took up some little frogs. So if you have 2 little frogs here, and these are my identical spheres, because what I had handy. And they have the same electric charge. So imagine they each have an excess of 10 electrons on each one. So they start out here. If their separation is doubled, so we move them twice as far apart, the force each exerts on the other will be. So without worrying about the numbers yet, we'll get to that in the second lecture for Chapter 16. But just think, if you have something close together and you move them further apart, do you think the force is going to increase or decrease between them? One way you might think about this, charge is not the same as magnets, but it might be easier to think of in terms of magnets, fields, and so on will be similar, is that these are both magnets and they're close together. You can imagine the pull on them if they're opposite polarities. And if you move them apart, you'd still have a pull, but it would decrease. And the same is true for the force for electric charge. When they're closer together, the force is greater. You pull them apart and the force will decrease. So that would limit your answers down to half, and then whether it went to being half as much or a quarter as much is something we can get to later on. Okay, let's move on from there. Okay, so static electricity. Static means things aren't moving, and electricity, as we see here, comes from the Greek word electron, which means amber. And that's because amber is a mineral that is easily given an electric charge. So my picture there is from my big fat Greek wedding, because the father of the bride there, shown on the right, says in the movie, all words come from Greek. Give me a word, any word, and I'll give you the Greek derivative of it. So in this case, he's right. Electricity comes from electron. Okay. So, static charge, let's just talk about what it is. We can charge objects by rubbing them. And once they're charged, no charge is moving. That's how we call it static electricity. We don't have a flow of charge. We'll get to that later. That'll be a current. But for now, we have a charged, we can charge an object and have it hold a charge. So one way to do that is by rubbing, and we call that the Amber effect or static electricity. And I'll show you a little demo. Here's a a little pile of pieces of paper like shown in the diagram there. Here's a plastic ruler. That ruler there, even though it looks wooden, is plastic. And if we touch the pieces of paper, they don't move. And then I have a piece of wool down here, and if I rub the ruler, I will do that, get it nicely rubbed up. And presumably I've now transferred excess electrons to the ruler, and if I put it near, they do, it attracts the little pieces of paper. So we have static electricity, and it's attracting them. And I can actually, if I remember, I can come back to this, and we may see that it loses its charge over time. But that's the idea behind static electricity. We can build up excess charge. In that case, I had excess negative charge or electrons in the plastic ruler after rubbing it. And then we can talk about why it attracted those neutral particles of paper as we move along. But you could definitely see the effect. There's something changed there, and we could see it. Okay, other examples. Combing your hair in the winter, especially if you have fine hair, can result in it standing on end. You can build up lint on clothing. You can have a spark when you touch a doorknob. Those are all examples of a buildup of static electricity, or in the case of the spark, it's then moving, but you built up an excess charge on yourself. Okay, once you have a charged object, how does it behave? So let's first talk about charge. It can come in two types, and those are named positive and negative charge. Benjamin Franklin was the first to refer to charges as positive and negative. This is probably something you covered in high school. Excess negative charge is an excess of electrons. Excess positive charge is usually a deficit of electrons, gives you a net positive charge. We can see why that is in a minute. Okay, so charges comes in two types, positive and negative. And what we can see is if we bring two objects together that are the same charge, then they repel each other. So likes repel. So if you go to the upper left image here, we have two negatively charged objects. We bring them near each other, and this object swings away. It is repelled. Likewise, if we bring two positively charged objects near each other, then this one will be repelled away, swings away. But if we bring two oppositely charged objects together, opposites attract. So you bring a positively charged glass rod near a negatively charged plastic ruler, then the two attract. This negative ruler will swing towards the plastic rod. So that's a really fundamental idea that you want to keep, that well, two of them there, that they're just two types of charge, positive and negative, and that opposites attract and likes repel. Okay. All right, and so with that, if we have positive and negative charge, Ben Franklin argued that whenever a certain amount of charge is produced on one object, say I get an excess of electrons on this plastic ruler, then an equal amount of the opposite charge is produced on the other. So if I have excess electrons here, I'm going to have a deficit of electrons or an excess of protons over here in relation. So the impact of that is that electric charge is conserved. Another way is to say that the net amount of electric charge produced in any process is zero, or no net electric charge can be created or destroyed. So you just have to be careful with the wording. It's no net electric charge can be created or destroyed. If I get extra electrons over here, I'll have a deficit of electrons or extra positive charge over here. Okay. So we have other conservation laws. We've had conservation of energy. We have conservation of linear momentum, conservation of angular momentum. This is our fourth conservation law, our conservation of electric charge. Okay, where does the electric charge come from? I've already alluded to this. I've talked about electrons, but let's get into let's get lightly into the details of that by talking about atoms. So here is a simple model of an atom. At the center is a nucleus. It's very small, it's dense, there's a lot of mass there, and it is filled with positive and neutral charge, protons and neutrons. And then in a cloud surrounding the nucleus are electrons. The cloud is large, but it's very low density, and these have negative charges. The electrons are negatively charged. So hopefully that's a review. You've seen models of the atom before. All right, and that's a simple model of the atom. By the end of the semester, we'll actually have a better model of a better understanding of the model of the atom. But that's a good start. So positive charge in the nucleus, negative charge in a cloud surrounding the nucleus. So an atom is shown there as electrically neutral, and then rubbing charges objects by moving electrons from one to the other. So it's the electrons that move. So when I rub the ruler with the cloth, and if I end up with an excess of electrons over here, I've taken excess electrons from the cloth and moved them to the ruler. So the electrons are what move. If I come back here and look again, you can see I had 3 positive charges or protons in the nucleus and 3 electrons in the cloud. That was a neutral atom to start off with. If that atom had been in our cloth and we had rubbed it, then some of these, maybe 1 electron per every few atoms, may have been removed and moved over to the ruler to get an excess negative charge over there. Okay, so rubbing charges objects by moving electrons from one object to the other. We start out then when we picked up the ruler and it didn't attract any little pieces of paper, the atoms were neutral. The number of protons equaled the number of electrons on the ruler. An ion is an atom that has gained or lost 1 or more electrons. So the number of protons now no longer equals the number of electrons. If an atom loses electrons, so you pluck an electron off of here, now you'd have 3 positive and 2 negative, you'll have excess positive charge, and you have a positive ion. If an atom gains electrons, you get an extra electron added to this cloud, then we have excess negative charge relative to positive, then you have a negative ion. Okay. All right, for a solid, like our ruler or our cloth, the nucleus tends to stay in a fixed position. It's rigidly held in place in a lattice, in a rigid framework for your solid. Then if you rub a solid, you can move electrons from one object to the other. For liquids and gases, the nucleus or ions can move as well as the electrons. So you can have a flow of a charged gas or a charged liquid, so you can move ions. Actually, that can happen in batteries. You may have ions moving through the electrolyte paste, which we'll eventually get to. Okay, why don't charged objects stay charged? So what happens over time? Actually, we can test right now and see if this ruler, now if I bring it back to these pieces of paper, it's not charged anymore. I could easily enough charge it up. I can rub it with the cloth and bring it back here, and it's charged again a bit. I could rub it a bit more and get more excess charge on there. But what happened? What happened to the charge? And it tends to leak off onto water molecules in the air. So if we look at a water molecule, it's a polar molecule, which means that overall it's neutral. There are 2 hydrogen atoms and 1 oxygen atom. That's your H2O, 2 hydrogen, 1 oxygen. We tend to get this polar molecule. You get excess positive charge sort of on one side of the molecule and excess negative charge on the other. So the charge is not evenly distributed. And so what happens? You get water molecules in the air. Our air is, there's oxygen and nitrogen and so on, but there also is moisture in the air, which is water molecules. And extra electrons, say on our charged plastic ruler, can leak off when attracted to the positive end of water molecules. So our plastic ruler gives up electrons to water molecules in the air. Or a positively charged object can be neutralized by the transfer of loosely held electrons from the water molecule to that object. So that's why objects that have static electric buildup don't tend to stay charged. Okay, And so why is static electricity going to be greater on a dry day? Or you could even say for a season, why is static electricity greater in winter? Well, in winter, the air generally is drier. If you're inside a house or inside the school, then you have excess, well, you have a lot of dry air being circulated by a heating system that tends to blow quite dry air, and there's less moisture in the air. If there's less moisture in the air, there are less of these polarized molecules available to help the charge equalize. So we tend to build up more static electricity on a dry day. Okay, let's take one more example. Common example for static electricity. If you walk across a carpet, electrons are going to move from the rug to you, especially if you're, say, in wool socks and you're walking across a carpet. So you shuffle your feet along the rug and you now have excess electrons on you. And then what can happen? You can touch a doorknob, which is metal. You could touch your friend in the shoulder, their nose, whatever. And electrons are going to jump from you with extra electrons to this neutrally charged objects. And you tend to get a shock in that exchange. So that's what's happening. Okay. Moving on, we're going to talk a bit about insulators and conductors. Insulators are things that insulate us from electric charge and can insulate us. And conductors are materials that can conduct electric charge. So if you have a conductor, charge flows freely in a conductor. Those electrons move easily from atom to atom. And most metals are conductors. In contrast, a non-conductor, an insulator, almost no charge flows, and that's most other materials. So if you have an electric wire and you want to make it so that you don't accidentally get a charge when wire is moving through it, you insulate it. So for instance, here's a wire for the base of my little microphone, and it has a plastic coating around it. And so that plastic coating will insulate the metal wire that's going through the core. Okay. Let's move. I'll get to those images on the bottom in a second. So in a conductor, the electrons are bound loosely to the nucleus and can move freely within the material. The electrons move easily from one atom to another. In a non-conductor, the electrons are bound tightly to the nucleus. They do not move readily. Okay, let's just go back here and consider two spheres. I can take my little frogs again. And let's say one is positively charged and one is neutral. Or let's make them look different. Let's make this positively charged and something different. Oh, I'll take a USB. All right. The frog has positive charge. The USB is neutral. If I connect them with, say, a metal nail, something that readily conducts electricity, well, I'll take this. Something that conducts electricity. If I connect the two, then charge can move through the conducting material, and you'll have that excess positive charge on the left be redistributed so it's evenly distributed between the two metal spheres. Oh, don't think that these are plastic ping pong balls, which they resemble. These are positive metals. These are metal spheres, so they can hold charge easily. Okay, so you connect them with a conductor and the charge moves. If you connect them with something that is not generally a conductor, and plastic is generally not a conductor, although we saw it can hold excess charge, but it's generally not a conductor, you connect those two and nothing would change. So you connect your positively charged metal sphere with another metal sphere with something like wood, no charge is going to move, and that stays the same. So conductor, charge moves, non-conductor does not conduct charge. Okay. So there are two ways that we can charge an object, and those are by conduction and induction. So in conduction, which is shown here, you start out with a neutral metal rod. You bring a charged object nearby. So this is something with a positive charge, and you allow them to touch. So the two objects touch in conduction. And so what happens? It's just like that example of the two metal spheres where one was neutral and the other had a charge. This one was neutral. This one has a charge. Charge flows. So in this case, electrons are going to move from this neutral charge and neutralize some of the excess positive charge here, and you'll get two positively charged objects. So the neutral rod acquires charge by contact. When you do this, you'll notice that both objects end up with the same charge after contact. All right, that's charge by conduction. And the two objects come into contact there, and afterwards both objects have the same charge. All right, in contrast, a little more involved is induction. And we start out with a neutral rod again, and it's going to ground. So there's a wire here connecting it to what we're going to call ground. And so you can imagine burying the wire in the earth, and the earth is so large and can conduct, it acts as a charged reservoir, so an object stays neutral. So we have a neutral object, it's connected to ground, so if there were any excess positive or negative charge, it would just interact with ground and it would stay neutral. So what happens? We bring a charged object nearby, but they don't touch. So you bring, say, a negatively charged object nearby, and what happens? We're going to have opposites attract or likes repel, and since the electrons are what move freely, the electrons are repelled and they move away. So they go to ground, and you end up with a positively charged object. With this charged, negatively charged object still nearby, I should be advancing. So bring a negatively charged rod near, it induces a positive charge in this previously neutral rod. So electrons move away, we have an excess positive charge here. While this rod is still nearby, we cut the tie to ground. So ground wire is cut with a negatively charged rod still nearby. Then we can move the negatively charged rod away, and we end up with a positively charged rod. So what do you see? The two objects don't touch in induction, and the newly charged object has the opposite charge of the object that was brought nearby. So those are a few observations. So two ways to induce charge, by conduction, where they come into contact, or by induction, where you bring something near, it repels, the nearby object is attached to ground, it gains the opposite charge to what was brought nearby, you cut the ground, and then it maintains the ground wire, and it maintains that opposite charge. Okay, so how can we use this? Let's say, I'm going to do one of the things first. So non-conductors won't become charged by conduction or induction because almost no electrons can move freely within a non-conductor. But charges can align within an atom or molecule. So you bring a positively charged object near a non-conductor, and all the negative electrons will be attracted. They'll be pulled towards that positive charge, but they don't move. They're locked within their atoms. But you can get things where we get an excess number of electrons sort of on the left side and, well, within each atom. So we can get them aligned within an atom or molecule of a non-conductor. Okay, so you can get a little bit of an attraction here. All right. All right, so what can we do with once we've induced a charge? How can this be helpful to us? And one way it can be helpful is to find out if something of a unknown object is electrically charged. And if we have something of known charge, we can figure out if that unknown object is positively or negatively charged. And we can do that with an electroscope. So an electroscope is shown here. We have a metal sphere at the top. There are two gold leaves attached to it, and they are held within glass inside this sphere, so we can't actually get at them and touch them with our fingers here, but we can reach this metal orb up here. All right, so two gold leaves. A gold leaf is just a very thin strip of gold material. Gold is a metal, so it's going to be a conductor. All right, so that's our setup for our electroscope, and we can do two things. We can charge our electroscope now by conduction or induction. So easy to do it by conduction here. Bring a positively charged, say an amber rod, up to the electroscope and put it in contact, and we end up with a charged, positively charged. We've simplified the view of the electroscope just with the sphere at the top and the two gold leaves. So the electroscope is now positively charged in that case. Okay. And so in our example, we're going to let it be negatively charged. It's unfortunate that the previous slide showed it positively charged. But just imagine we brought something negatively charged nearby. We put them in contact. We start out with a negatively charged electroscope. So our electroscope is already charged, and now we have something of unknown charge. So we have this green object and this red object, and they are unknown charge. And what happens? If you bring something that has the same charge as the electroscope, then likes are going to repel. So you bring, say, something with excess electrons here, it's going to drive the electrons further away. So we get extra electrons here in the gold foils, extra electrons there, likes repel, and the gold foils move apart. So as opposed to the electroscope just sitting here happily on its own, you bring something of the same charge nearby, the gold leafs move further apart. Bring something of the opposite charge nearby, opposites attract, all those electrons come moving up into the top of the electroscope, and we have a relative deficit of electric charge down here from before, bringing the red object nearby. And so with less extra electrons down here, there's less repulsion, and the gold leafs relax a little bit. So they're a bit further together. So bring something of the same charge nearby, the gold leafs move apart. Bring something of opposite charge nearby, and the gold leafs move closer together. So that's how we can, and if you brought something nearby that wasn't charged at all, then there wouldn't be any change to the electroscope. Notice also that we didn't allow things to touch here because we don't want charge moving. Then we wouldn't be able to say anything about the green object or the red object. If we allowed it to touch the electroscope, then we'd have charge moving, and we wouldn't know what the effects were due to, whether it was due. And so we wouldn't know. So you just want to bring it nearby but not touching in order not to complicate things by having charge move between the two objects. Okay, that's it for beginning of chapter 16. And come back in a little bit and we will do the second half of chapter 16. Thanks. Bye.